Hello, in this first video about generative adversarial networks, I will talk about the fundamental concepts of GANs by discussing the paper Generative Adversarial Nets. One of the main building blocks of GAN is generator. The generator aims to produce data which cannot be distinguished from real data. To achieve this, the generator starts with a random input, often sampled from a simple distribution such as uniform or Gaussian. This random input, denoted as Z, is passed through the generator neural network, which has its own set of trainable parameters referred to as W sub G. The generator learns to transform this random noise into data that resembles samples from the real data distribution, such as images. Next, we have the discriminator block, which is responsible for distinguishing between real and generated data. It takes an input either from the real dataset or the generator and outputs a probability indicating how likely the data is real. Ideally, the discriminator outputs a value close to 1 when the input is from the real dataset, and a value close to 0 when the input is generated by the generator. When the generator produces data g of z, both the real data and the generated data are fed into the discriminator. Based on the discriminator's output, we update the weights of both the generator and the discriminator. This allows the generator to improve its ability to create more realistic data, while the discriminator becomes better at distinguishing real from fake data. So, the generator's objective is to fool the discriminator. In other words, it aims to maximize the probability that the discriminator classifies the generated data as real. This can be expressed as maximizing log of d of g of z, where d of g of z is the discriminator's output when given the generated data. Alternatively, the generator tries to minimize the probability that the discriminator recognizes the generated data as fake, which is this expression. On the other hand, the discriminator's goal is to maximize the probability of correctly identifying real data and simultaneously maximize the probability of correctly detecting generated or fake data. We can now express these objectives in terms of loss functions that both networks aim to minimize during training. The discriminator's loss function consists of two components. The first term calculates the expected log probability that D correctly classifies real data X as real, with the goal of achieving a value close to 1 for minimal loss. The second term evaluates the expected log probability that discriminator identifies the generated data as fake, where we want d of g of z to approach 0 for minimal loss. On the other hand, the generator's loss focuses on minimizing the term related to d of g of z, indicating that on average, the generator aims for the discriminator to classify its generated data as real. Consequently, if d of g of z approaches 1, the generator loss decreases. This dynamic encourages the generator to produce increasingly realistic data that can successfully deceive the discriminator. During training, we process mini batches of data instead of calculating the expected value over the entire dataset. Therefore, we compute the loss functions for a small, randomly selected subset of data. For example, here M is the size of the mini batch. Now we can calculate the gradients with respect to the network parameters W. For example, for the generator, we can apply the chain rule to differentiate the loss with respect to parameters of the network W. This involves differentiating the loss of G with respect to G and then multiplying it by the derivative of G with respect to W. Now we can use the differentiation formula for the logarithm, which gives us 1 over d of G of Z multiplied by the derivative of d of G of Z with respect to G of Z. For the second term, we take the derivative of G with respect to its parameter W. As we can see, for the generator, we don't have direct access to the outputs to update the gradients. Instead, the output of the discriminator provides critical feedback that guides the generator in producing more realistic data. This visual graph illustrates the training process of a GAN. In these figures, the black line is the distribution of the real data. Green line is the generated data from the generator G, and blue line is the output of discriminator D. In figure A, G is mapping the Z samples to a location in data space that does not accurately represent the concentration of real data. D can differentiate real data, indicating by higher probability from the generated data, although it does so with some uncertainty. As the samples get closer to the generated data, D outputs a lower probability, indicating it recognizes the data as fake. In figure B, we see that D has been updated and can more confidently distinguish between fake and real data. In figure C, guided by the D's feedback, G has learned to map the input noise to a better location in the data space, producing samples that more closely resemble the real data. Finally, in figure D, G has successfully found the mapping that best resembles the real data. At this stage, D is confused and assigns a probability of 0.5, indicating it cannot determine whether the data comes from the real distribution or the generated distribution. While this straightforward approach has its advantages, it also presents several challenges that later methods have addressed, which I will discuss in future videos. One major challenge arises when the generator G discovers one or few outputs that are good enough to successfully trick the discriminator D. In this case, G may begin to ignore other variations and produce only those specific samples, resulting in a phenomenon known as mode collapse, where the generator outputs a limited range of data. Another issue occurs when D is not updated frequently enough. If D falls behind, it struggles to distinguish between real and fake data accurately. This situation leads G to operate with outdated feedback, causing it to focus on a narrow set of outputs that D has yet to learn to identify as fake. Therefore, a balance between D and G is crucial. If G advances too quickly in training, it can exploit weaknesses in D's classification capabilities, further contributing to mode collapse. Another challenge is the problem of vanishing gradients. At the beginning of the training process, when D can easily differentiate between real and fake data, the gradient signal used to update the generator's weight can become very small. This results in minimal updates to G, limiting its ability to improve and generate more diverse outputs. That's it for today's video. See you in next part of GANs.